Okay, so I hope everybody can find my recording online. If you want to go back and check it out, or if you have other reasons, if you miss a class, do make sure you listen to the recording and don't get fall behind. So, starting from today, we're gonna talk about chapter 4, or the very, very fundamental of quantum mechanics. And eventually we'll see how that quantum mechanics related to chemistry, right? We need to understand what is an atom before we can start talking about chemical bonds. So for today, we'll start by talking about black body radiation, and then we're going to spend a little bit of time talking about why classical physics fall for black body radiation. For that purpose, you'll also need to learn how to read a scientific graph, how to read a complicated reaction. Like, don't get frightened by those equations and graphs. And then at the very end, we're going to introduce one of the central hypotheses for quantum mechanics, which is Max Planck's quantum hypothesis. And we'll see how the quantum hypothesis actually solved the black body radiation problem. All right. Before we get started, a quick review. So on Wednesday, we went over the classical physics and a little bit of calculus, right? What is a derivative? What is an integral? And the bottom line here is at the end, we came to the conclusion. In classical physics, we know that energy is continuous. By saying energy is continuous, means that at any point x, right, your energy or your potential energy can take any arbitrary value. So this is what we call an energy diagram. So on the y-axis, just one dimension, right, just the energy. And we see that in the classical oscillator, everything is continuous. Your energy can take any number depending on where your x is. And your x can also take any number. Okay, so now let's move on to black body radiation. So before we talk about the failure of black body radiation, we need to know what is black body radiation. It always sounds mysterious, but in reality, black body radiation is just stating a simple fact. What it's saying is that all objects, as long as it has a temperature, will emit energy from its surface in the form of thermal radiation carried by electromagnetic wave. So that's related to thermochemistry, classical thermochemistry. A little bit of the extra, if you're really looking into the physics, like what exactly causes the black body radiation, is that on the surface of any object, you always have electrons, you always have protons. All these charged particles, they're oscillating because they've been accelerated by thermal energy. So when we say thermal energy, we're talking about as long as an object has temperature, as long as it's above absolute zero, right, above 0K, it will always have some thermal energy. And that energy is going to accelerate your particle. And remember, we talked about in classical theory, when you have an accelerated charged particle, it will release electromagnetic radiation. And that's taken together, that's the origin, the physical origin of black body radiation. Nothing fancy, it's just what we talk about. Charged particle with acceleration release electromagnetic radiation. Some of the example here is, well, again, black body radiation is not mysterious, right? The sun, we see sunlight because it's also giving out energy as black body radiation. And the wavelength or the type of electromagnetic radiation that's given out depends on the temperature. You'll probably see that question in your discussion worksheet. So for example, as the sun has a very high temperature, 5,500 K, it releases electromagnetic radiation in our visible light spectrum. So that's why we can see different color. Alternatively, for room temperature objects, it gives out electromagnetic radiation in the infrared region. So far so good, right? This is just a quick introduction into what is black body radiation and how people used to think about black body radiation. Just on the surface of any object, as long as it has a temperature. The charged electrons, they are accelerated by thermal motion. By thermal motion means it has a temperature associated with it. So when your charged particle is being accelerated, it's releasing electromagnetic wave. And that electromagnetic wave is the black body radiation we observe. We see that all the time, right? All over the place. That's from the sun, or from any objects, or a light bulb. All right, and then that's what we see. That's an experimental observation. And now we're moving on to how do people actually develop theory to describe the black body radiation. So let's look at the classical theory first. So I'm just showing here in the very, very fundamental classical model, talking about the intensity of the black body radiation. We'll look at what is intensity here, but here's the equation that we're showing. In here, we have 8 pi, these are just constant. Kb, that's constant. For an object at a certain temperature, T is also constant, right? C, that's the speed of light in vacuum. And the only variable here is the frequency of that radiation. So before we move on, I'm going to spend a little bit of time just looking at this seemingly complicated mathematical expression and how can we get physical meaning from this equation. So let's take a closer look on the actual unit that's being used in this equation and get an idea about what's the physical meaning of black body radiation intensity here. So in this case, let's start from our first constant, Kb here. So that is our Boltzmann constant with the unit of meter square, kilogram, second, and K minus 1. Or the first part, you can just think about that as the energy. Or it's equivalent to say, Kb has a unit in joule per Kelvin. All right, so that's one of our Boltzmann universal constant. It's called Boltzmann constant. Right, so this is for our Kb. And then for temperature, the SI unit for temperature, that's K, that's Kelvin. So if you don't already know, Kelvin is defined, say, when you have 0 degrees Celsius, you have roughly 273.15 Kelvin. And 0 Kelvin is what we call the absolute zero. All right, moving on, we have the frequency. This we discussed on Wednesday when we were talking about the wave. So that has a unit of S minus 1. So that's frequency. Remember, that's how much wave is passed in a certain given time. All right, and then we have the speed of light. That's meter per second. And in here, we have a pair of universal constant and temperature unit, if you may. So, taking that together, we can now write down the unit for the intensity here. So I'm just going to copy-paste the equation for your reference. And if we're just ignoring everything, we just look at the unit. What we have here for the Kb, the Boltzmann constant, that's joule per Kelvin. For temperature, that's Kelvin. For frequency squared, that's S minus 2. And on the bottom, we have m third S minus 3. And we can cancel out some of the terms, right? So the Kelvin and Kelvin cancel out. And this minus 2 and minus 3 ends up to be just minus 1. So taking together the unit of the intensity for black body radiation, you can write it as joule second and meter per minus 3. Or if we want physical meaning from it, that's joule minus 3 and S minus 1 on the bottom. So the reason we write it here is we want to put what is the physical meaning of the intensity. That tells you the energy so that's where this m minus 3 comes from. Yes. Oh yeah, it should be positive 3 on the bottom, sorry. Nice catch. And per frequency. Right? So this is just an example when we're having a complicated equation, when we're having a complicated mathematical expression in physics. How do you actually get physical meaning out of it? And what we're getting here is you can imagine the black body radiation is a form of energy that's defined in the energy per volume per frequency. All right, so it's some type of energy. It's not exactly in joule, but we're talking about energy here, or we're talking about intensity. All right, so now we can move on and keep looking at this classical model once we know the physical meaning of the intensity. And let's just think about it from common sense, what may have gone wrong in the classical model for black body radiation. So here is, I'm just writing down my equation 1, the classical expression for black body radiation here. And I'm plotting this classical model on my graph. So what we have on this graph, on the y-axis, we have the intensity. So remember, that's energy per volume per frequency, right? So we're talking about some type of energy. On the x-axis, it can be lambda, or which is wavelength, or frequency, which is so wavelength or frequency, both can work for this x-axis because they're interconverting. They're just connected by the speed of light. So here I'm just using lambda as an example. And looking at this figure here, again, we have all these terms being constant. What that means is we're expecting the intensity as a function of frequency or wavelength is directly proportional to the square of frequency at constant t. Right, so if you think about it, when you have large wavelengths, you have small frequency, and you're expected to have small intensity. Alternatively, when you have small wavelength, you expected to have a large frequency and a very large intensity. All right, because it is proportional to the square of frequency. So that comes to a certain point, which you may start to feel something is wrong with this model. So if you think a little bit stronger here, right, I'm just writing this down, what we are talking about, because the speed of light equals to wavelength times frequency. So what we have is when lambda, the wavelength, approaches 0, my frequency is going to approach infinity. And since we just deducted in the classical model that the intensity is proportional to frequency squared at constant temperature. So the weird part of my classical model becomes the classical model predicts that my intensity is approaching infinity when lambda is small. So that's when we're talking about lambda, the wavelength is small, we're talking about ultraviolet, X-ray, and gamma ray, and so on. Or in general, these high energy radiation that can harm your body. So that's actually come up with a big failure, even we're talking about common sense, because we know like ultraviolet radiation exists, we know X-ray exists, right? But at those low wavelengths region for high frequency, we don't have infinity amount of intensity or very high amount of intensity of black body radiation that's just burns everybody out. So that's just wrong from common sense. And moreover, on top of the common sense, the experimental observation also fits our common sense, but doesn't fit the classical model. So this is what the experimental observation is. I'm going to show you the cartoon version and the actual figure right after. So what we observe experimentally is we have the intensity, the rho t mu, which is a function of frequency, actually falls to 0 at very short wavelengths. All right, so this gray curve here, that's our predicted curve from pure classical theory. Right, so I have it here, right. So the gray curve, that's our pure classical prediction. And what the actual observation is showing in red here. So what we have here is a clear inconsistency between the theory prediction and the experimental observation. And since it's always like the experimental observation normally peaks at the ultraviolet region, the scientist gives a name called ultraviolet catastrophe. All right, so quickly pause here. I mean, this is one of the examples in how you can use what you know, which in this case, we start from the experiment, the classical prediction, classical model for black body radiation, which is 8 pi kBt mu square over c third. And then we look at the experimental observation, and we come to the point and say, all right, so the classical model simply doesn't work to explain the black body radiation. And you want to know why it doesn't work, and that goes back to what we just discussed before. So you could expect one of those questions in your discussion or your homework or your exam, saying like, okay, so explain to me what is an ultraviolet catastrophe and how do we understand it? Like, why is classical theory failing for explaining black body radiation? Okay, so that's a cartoon version, right? And now I'm just showing you some of the real graph from your textbook, which is the same idea, right? So you can read it. The dashed line here, where the classical predicted curve at different temperature. In this case, we have 5,000 Kelvin or 7,000 Kelvin. And none of them fits the actual experimental observation, which are shown in the solid curve here. Right, so that's just the real spectrum of what we just saw before, the ultraviolet catastrophe. So now we have a situation. We have classical theory, and we have experimental observation. They don't agree with each other. So for scientists, it's unfortunate, but what that means is whenever you have a theory that doesn't fit your actual experimental observation, means something is wrong in your theory, something is wrong in your fundamental hypothesis when you're developing the classical theory. All right, so that's the end when we're talking about the failure of the classical mechanics in explaining the black body radiation. Let's see if we have any questions before we move on to the quantum part. Yes?
So when you say that the intensity is the energy of the wave per volume of frequency, what is the volume that it's moving through?
Okay, so the question is, what exactly is physical meaning of intensity? What we're saying is energy per volume per frequency. I think the best way to understand it is you can imagine a box. It's just sitting there. And intensity basically say, now you're counting how much energy is reached in this box per frequency of the radiation. So the bottom line is, it is a little bit more complicated. The intensity is a little bit more complicated than just simple energy, but it's very much related to energy.
So do we know what type of energy it is, or do we just know it's energy?
Well, let's just accept it is energy, and then we'll talk about how energy is related to frequency and in electromagnetic radiation too. Let's see if we have more questions. Okay, so now we're getting into the exciting part. We're talking about quantum mechanics, right? So the classical theory doesn't work. So that's why we need quantum mechanics. So here we have the one fundamental hypothesis for quantum mechanics, which is originally proposed by Max Planck. I'm just going to read it here with you. It is saying, it is not possible to put any arbitrary amount of energy into an oscillator of frequency mu. So again, when we're saying oscillator here, it's not any definite style of oscillator. It can be a spring that's oscillating, it can be a chemical bond that is oscillating, or it can just be an electron that's oscillating around. So when we're talking about an oscillator, don't think about it as any specific type of oscillator. It's just in general, in quantum mechanics. When we're talking about energy, they can't take any arbitrary amount. Or the more mathematical way to think about it is an oscillator must gain or lose energy in small packets of magnitude of h mu. So if I write it out, is in quantum mechanics, we have E oscillator equals to N times H mu, where N is are integer numbers. And in this relationship, H is my Planck constant, which takes the numeric value of 6.626. I'm just going to write it all down, but you probably don't need all that thick fig when you are solving questions. Times 10 to the negative 34 joule second. And that is our Planck constant. It's one of our universal constants. So what does that mean? Now we have an equation, we have a hypothesis. What does that mean when we're looking at the energy diagram for Planck's quantum hypothesis? So again, this is a reminder of what we did this Wednesday when we're talking about the classical oscillator. What we have are energy levels can take any arbitrary numbers, right? So this process is a continuous process. So energy is continuous in classical theory. Alternatively, now with the quantum hypothesis, remember we're saying the energy level cannot take any arbitrary number. It needs to gain or lose energy in small packets. So what that means when we're drawing out the quantum version of my energy diagram, again, it's one-dimensional. We're just talking about what are the possible ways the energy can change. So that's the lowest one. We have n equals to 1. And second one is 2h mu, 3h mu, and so on. Because remember, like E oscillator equals to n h mu. And n can only take integer numbers, and so on. And if we look at the difference here between each step, that is a small packet of energy, and that's the minimum step your oscillator can take when it's gaining or losing energy. So that's our fundamental hypothesis. Okay, and let's see how does our quantum hypothesis, how are these small energy steps actually help the scientists to solve the blackbody radiation problem. So now, with that hypothesis in mind, what we have is an updated quantum picture for the blackbody radiation. So let's just look at it together. What we have here on the left-hand side, we still have constant 8 pi h and c third, that's constant. But on the right-hand side, we now have this peculiar exponential term. So what's the physical meaning of this exponential term? So let's just look at some of the things here. Firstly, we have our h mu. So remember, in our quantum picture, h mu, that's the smallest step your oscillator can gain or lose energy. All right, so let me write it out again. So that's minimum energy required to activate an oscillator of frequency mu. So if you go back to this picture here, right? So imagine your oscillator is originally in the lower state, h mu. The smallest amount of energy level it required is at least h mu. All right, so that's just one step, the smallest step your oscillator can take. Alternatively, on the other hand, we have this KBT term. So we saw the unit for KB, and that's joule per Kelvin. And for temperature, that is in Kelvin. So without going into too much detail into thermodynamics, what we have is we know that KBT is a form of thermal energy. All right, because of the unit cancel out to give you joule. So this means KBT, that's the amount of thermal energy available at temperature T, because T is a constant. So what this exponential term gives us is actually a probability. What that means is, if I write it down, is at any given temperature, the amount of thermal energy, KBT, is a fixed value. All right, so at given temperature, my KBT is just a constant. It's not changing. And now the oscillators at the surface. So remember before when we were talking about oscillators at the surface in classical theory, it doesn't matter how much energy you have. It will always be somehow excited with some acceleration. But now it says, because we need those small gaps for the oscillator to be activated, so now it depends on if you have enough energy, enough thermal energy available at the temperature, these oscillators may or may not be activated. May or may not have sufficient thermal energy to excite to high frequency, to high level, higher energy levels. All right, so let me just put this down here, and then we can look at a graphical representation. Okay, let's see. Yeah, this part is a little bit less counterintuitive. It's a little bit counterintuitive, so let me just put it down. Okay. And now let's look at a graphical representation, and I hope it's going to help you understand it a little bit more. So let's imagine on the surface here, for a certain frequency mu, we're trying to excite this oscillator from a lower energy state, say h mu, to 2h mu. So when you have a higher frequency oscillator, right, so when we're at the ultraviolet region, we have a higher frequency oscillator. We're expecting this delta E of the smallest packet, or h mu, to get larger. So we're talking about how likely it is being activated from h mu to 2h mu at kBt. And then at finite temperature, my kBt is constant. Right, so when we're talking about this delta E, we're talking about that being related to a probability. So depends on your frequency, right? So we're talking about at the higher frequency, these oscillators have lower probability being activated. So that is why, going back to the black body radiation, at the high frequency region, we have not as much oscillator being activated as the lower energy, lower frequency region. All right, so that takes back to our final conclusion here in how the quantum hypothesis contribute to the black body radiation. As we're talking about the fall off in the intensity with high frequency is due to a diminishing probability. So this term here, this is a probability term. Of exciting the high frequency oscillators. So the higher your oscillator frequency is, the more energy it requires to be activated, and the less likely it will be activated at a given temperature. Okay, I'll give everybody a little bit of time just thinking about this through and see if we have questions. Let's see if we have questions. Yes?
Can you repeat again why higher frequencies leads to lower probability?
Right. So the question is, why is higher frequency leads to lower probability? So here, that's what this exponential term is doing. When we're taking the ratio here, it depends on how big that is. It gives you a probability back. So that's the math part I'm not talking about. But what I want to focus is what exactly we're talking about. We're talking about the ratio between the thermal energy available and the energy step that's required to excite an oscillator. Right, so we're talking about this gap here, the smallest gap, delta E equals to h mu. So when we're having a higher frequency oscillator, it means my mu is bigger, and then my h is a constant. That means my delta E is gonna get bigger, right? But when this delta E is getting bigger, my thermal energy is a constant number at given t, right? kBt, that's a constant number. So the energy gap gets bigger, you have lower probability of having enough kBt to activate to that higher energy level. So that's where we come to the point, how does this quantum hypothesis helps explaining the black body radiation, right? So the higher the frequency is, the lower the wavelength is, this delta E gets bigger. So at constant thermal energy, kBt, it has lower probability being activated. Yes?
How does lowering the probability change, like lower the intensity?
Right, so if we go back here, what this term is going to do is when the probability is approaching zero, That means at the high frequency value, when the probability is approaching 0, the intensity is expected to approach 0. So that explains the catastrophe. We'll see a fitting of the actual quantum model to the experimental very soon. Yes?
Are those two multiplied?
Yes, these two are multiplied by each other. I just didn't write it out. Okay, and let me show you one more example, and I hope that's going to help you understand it a little bit more. So let's look at a hypothetical situation. So now imagine we're not in the real universe we're living in. We're in this universe where you have infinity temperature, where there is an object has infinity temperature. This is where the quantum and the classical theory actually meets with each other. All right, so when you have an infinity temperature, means your thermal energy is infinity. Again, that goes back to your classical model, right? Whatever the energy gap is, you always have enough thermal energy to activate it. So what will that equation looks like? So let's do that together here. So let's say now we have temperature approaches infinity. Again, this is going to use a little bit of calculus. If you're not so sure about it, it's okay. I'm not going to ask you to derive it. I just want to show you how that's being done. So when temperature is approaching infinity, what we have is this exponential term, h mu over kBt. We can roughly write it as 1 plus h mu over kBt. Again, it's a Taylor expansion, and in this case, the temperature is approaching infinity, and this term, the following term, becomes very, very small. So that's why we can just keep the first two terms here. So what that gives us, I have that original equation showing up there, is the rho T mu is roughly equals to h pi h mu third c third times h mu over kBt plus 1 minus 1 and over 1. Right, rewrite the term a little bit. We have the 8 pi h mu third c third. That's kBt and h mu. And obviously we can cancel out some of the term here. And what we end up with is 8 pi kBt mu square c third. Again, what it means, now we're getting back to our classical equation here, right? So that's our classical equation. So what we're talking about here is at infinity temperature, all of your oscillator, whatever your frequency is, can be activated. All right, so the reason at infinity temperature your classical theory meets the quantum theory is now we don't care about how large that energy gap is. You always have enough energy to activate it. Whether in reality, you don't have infinity thermal energy. So when your frequency gets big, the probability of activating that oscillator and give a black body radiation becomes really, really small. So that goes to the last bit here. So here, again, we have a new theory, and we need to validate it. So I'm just showing here the experimental validation of Planck's equation, which I showed up there. I don't know where that comes from. Okay. And now what it's doing is the dots here are the measured intensity. The dots are the experimental observation. And the red curve here is the predicted intensity from Max Planck's mu equation here with the quantum hypothesis. And again, just want to remind everybody in here what we have, this part. This talks about the probability. All right, so that gives you how likely an oscillator is being activated with certain frequency mu at a given temperature T. All right, questions before we move on? Any? Yes?
When you say to be activated, it needs to go up to one energy level, correct?
Yeah, so when I say activated, basically if we go back to the energy level, it can go 1 or 2, but the smallest gap it can take is just 1 energy gap.
Can you go back up to like where you said T goes to infinity?
So going back to T goes to
How did you get 1 plus?
this one? Oh, that's going back to calculus. That I don't expect you to know, but if you know calculus, you'll see that's just a Taylor expansion of your exponential function. Yes?
When you were talking about N, like these stages, can N be negative?
So here, the question is, can n be a negative number? So the answer is no, we don't have negative number. The smallest it can be is at least 1. So the n starts from 1. You can't have negative energy, so that's why n can't be a negative number here. Okay, so far, what we did is already pretty incredible, right? We start from blackbody radiation. We talk about the classical model we use to describe blackbody radiation. How does that classical model fail? And then we move on to talk about the quantum mechanical model, and we came to this fundamental hypothesis in quantum mechanics, which is in quantum mechanics, energy levels are discontinuous. The smallest gap you can take for these energy levels is at least h mu. So now the question begins. Before we end, I just want to quickly show you some more application, or just think it a little bit more through. So do we have energy quantization? Well, we're talking about classical oscillator, like for our macroscopic world. Why we don't see energy quantization? You feel like you can move your hand and anywhere, you don't feel like I need to go like at every step, right? So we can just do some quick calculations and see why we don't see quantum effects in our macroscopic life. So again, I'm just using the Hooke's law and this little ball on a spring. I'll give a simple example. Let's imagine the frequency, mu, is about 1 hertz, means that ball just oscillating every second. So the E oscillation that's in quantum hypothesis is NH mu, where n equals to 1, 2, 3, and so on. So what we have for each step of this classic oscillator, my E oscillator is, delta E oscillator for each step is h mu, which about 6.626 times 10 to the 34 joule. So the Planck constant is a very small number. So for thinking about just this macroscopic oscillator that's vibrating every second, so your each step is 6.626 times 10 to the negative 34 joule. So in comparison, if we put this ball and we move it a little bit, attached to a spring with the stiffness is 1 Newton per meter, and let's say the displacement is 1 meter. And this part, we have the potential energy equals to 1/2 k x minus x0 squared. That gives you about 1/2 joule. So if we compare these two numbers here, what it means is that these quantized steps are just simply too small to be observed. So we don't have a scale that is accurate enough so we can see these quantized steps in our everyday life. And you just don't feel it, you're not sensitive enough to feel those quantization in your real life. All right. So I hope this is a good introduction for everyone for blackbody radiation. And now you know why energy levels are quantized. And in next Monday, we have the holiday. And next Wednesday, we'll be talking about photoelectric effect. And we'll be talking about how light can behave as both a wave and a particle. So wave-particle duality, that's the second hypothesis for quantum mechanics. All right, that's all.